Welcome everybody to Welland Public Library's presentation of Roving, Mars and Earth. Our guest speaker tonight is Mariek Schmidt. Mariek is Associate Professor of Earth Sciences at Brock University. She's a geologist who studies igneous and volcanic rock from Earth and Mars. And she's worked on 3 rover missions and most recently on the Mars 2020 mission. She's going to talk a bit about that tonight and talk about the latest developments. And I think she's going to share some interesting stories, maybe some pictures, and I'll leave it to her. So Mariek, all you.
Okay, thank you. Thanks everyone for coming to this evening. I just need to share my screen. Okay, can everybody see this? I'll take that as a yes. Is that right? I see a thumbs up. Thank you, Paula. Okay, so I'd like to start these talks by giving a brief, self-introduction, even though Marla just did that as well. So I am a volcanologist and igneous petrologist. I work on both Earth and Mars. And so I visit volcanic fields in various places. This is a photo of me in Iceland, and you can see a smaller volcano here off to my, off behind me. And then there's actually a larger volcano. It's a caldera in Iceland, Askja volcano. And then I'm also a professor at Brock University. And so I bring graduate students out in the field with me. And this is a photo of me and a couple graduate students in Central Oregon. And so they get to do research with me on Earth, as well as working on rover missions. I'm also a mom, and you might hear my 3-year-old behind me in the other room. So I have a 3-year-old and a 6-year-old. Both are, it's fun to share what I do with them. So my 3-year-old loves to dress up like an astronaut and talk about space. And my daughter Amity, who's 6, always has her head down to the ground, looking through gravel, looking for just the right crystals. And her room is just decorated with lots of colorful rocks. Okay, so but what brings you guys here today is Mars, right? So the big question of why we want to study Mars, and the big question is, can we find evidence that life occurred outside of the Earth? Okay, and this is what fundamentally drives a lot of our exploration of the red planet. So the reason why this is interesting is that we know that life thrives on Earth. But there's this question about whether or not other planets could possibly be habitable. So to explain this, I have a plot that shows stars on the left. And you can see the largest star at the top and the smallest stars at the bottom. And our sun is actually a very average sized star. And then we have the planets that are trending off away from them. And you can see that this blue zone represents a region where we think that life can exist. And we know that Earth is very happy there, that life on Earth is very happy there. But Venus is too hot. And you can see, though, that Mars is just outside of this habitable zone. But there's enough reason to suspect that habitable zone could have once been extended at an earlier time in Mars history. So when we compare Earth and Mars side by side, you can see that there's 2 big differences. One being the size of the 2 planets. So Mars is smaller than the Earth. It's about 2/3 the size of the Earth. Sorry. Another big difference, though, is the presence of liquid water on the surface of Earth, and there's no liquid water on the surface of Mars today. But there's evidence that at one time there was liquid water on the surface of Mars, and I will get to that later on. But first, let's talk about this size difference. Okay, why this size is important for the Earth. There's a number of different reasons, but one of the reasons why life is able to thrive on Earth is that we have the planet is hot enough in its interior. It hasn't cooled down too much, and the size allows it to stay hot, allowing us to have a liquid outer core. And that liquid outer core is what generates the magnetic dynamo, and it gives us a magnetic field. And that magnetic field is very important because it provides a shield for our planet from solar radiation. Okay, so Mars is small. It does not contain a liquid outer core today. However, there is evidence in the rocks, in the rock record that has been seen from orbit, that in the past, there may have been a magnetic field in the past. Okay, and that's because early on in Mars history, it was a lot hotter when the planet was formed. And so over time, it cooled down, but early on in its history, it could have been hot enough to sustain a magnetic dynamo in its interior. Okay, the other big difference that I mentioned is the presence of liquid water on the Earth. And to explain this, I show here what's called a phase diagram. Okay, and what is shown here is we have pressure on the y-axis, so along here, and temperature here. And there are 3 different phases for water that are stable on Earth. And so you guys know these as ice within this field. And then with increasing temperature, we have liquid. And then at higher temperatures, we have a gas that is stable. Okay, and so on Earth, where we have a nice stable atmospheric pressure, it's represented here, and we know this temperature where ice goes to liquid as the melting point or the freezing point, and where it goes from liquid to gas as the normal boiling point out here. Okay, so Mars has a lower atmospheric pressure, and that's in part because of its size. It's lost its atmosphere. So it has a lower gravity, force of gravity. It doesn't hold on to its atmosphere so as strongly. So it's actually lost its atmosphere to space. So it's a lower atmospheric pressure today. It still has an atmosphere though. And so we sit here right at this region of low pressure, where we go from a field of ice straight into a gas, okay? And as you increase temperature. However, early on in Mars's history, we think that the atmospheric pressure was greater and that we could have occupied this space where liquid water would have been stable, okay? So on Mars today, there is evidence of ice in multiple forms, such as at the polar ice caps. We also see water ice in clouds around the planet as well. So ice is certainly there. We know that we have gas as well because there's water vapor in the atmosphere. Okay, so how I have worked on Mars has been through experiences with participating in rover missions. And the first rover mission that I got a chance to participate in is the Mars Exploration Rover mission. And the objective of this rover was to find evidence of past water. It landed in 2004, and there were 2 rovers. The most recent rover, Opportunity, continued to drive around the surface of Mars up until 2018. So these guys were really long-lived. This rover, it has some features of it that are pretty similar to later rovers. It's a smaller size, but all the rovers that I'm going to show you have 6 wheels. They have a mast to it where there's cameras and other instruments on it. So it will have a left and a right eye camera that will allow the rover to take stereo images. And this allows us to drive around the surface of Mars. There's also a power source. So for the Mars exploration rovers, this rover has solar panels. The later rovers that I'll talk about are nuclear powered. And then there's also these things that stick out. These are high gain antennas that allow the rover to communicate both with Earth, directly to Earth, or with orbiters that are circling Mars. And so there are a number of missions that are in orbit around Mars today that we can communicate with the rovers. Another thing about these rovers is that they will have an arm on them with a suite of instruments at the end that we can deploy the arm and lay it down on a rock and analyze the rock's chemistry and its mineralogy. Okay. So I was fortunate to be a postdoc on this mission. And so you can see here I am at the Jet Propulsion Lab. This is what's called the test bed rover that they use for testing driving and other kinds of things at the lab. And you can see that it's a smaller vehicle. It's about the size of a small golf cart, I would say, even though I am standing off away from it. So there are two rovers. The first rover, Spirit, was sent to a place called Gusev Crater. And why this place was selected is that this crater has a stream channel that empties into it. And so we could tell that at one time, liquid water went over the surface in this area and emptied into this crater, filled it up. And then at one time, there was a lake at Gusev Crater. The other rover that we were interested in I worked with was the Opportunity Rover. And the Opportunity Rover was sent to a place called Meridiani Planum. Opportunity was sent to this location, not because of the shape of the surface, but because from orbit, we could see that there was an abundance of the mineral hematite present. So hematite is an iron oxide mineral. And it's basically, you can think of it as rust, okay? So oxidized iron. And we know that this is a mineral that forms in the presence of water. So we use the mineralogy to interpret the geology and say that if we're gonna look for evidence of past water, this is a good place to look. So first, let's talk about Spirit. Spirit was active until 2010, and when it first landed in Gusev Crater, it encountered a lot of lava rocks. That was actually kind of a disappointment to some people on the team, because the lava rocks, they didn't show evidence of interaction with water. However, as the rover progressed and as it continued on, we did see evidence of that. And the site where we saw abundant evidence of interaction with water is this place called Home Plate. So Home Plate is an outcrop that's about 80 meters across. And in yellow, this is the rover's traverse around Home Plate. So when we encountered Home Plate, what it looked like, this is what it looked like from the side. And you can see these layers of rock present here. And we interpret this outcrop to have been formed by explosive magma water interaction. So it is, the chemistry of this rock is very similar to the lavas, but it's fragmental. And it contains textures that are indicative of having interacted with water explosively, okay? And the easiest thing to point out to you guys is this feature here that I'm circling. Here is another view of this feature. So what you see is a 3 centimeter wide rock here. It is included within the outcrop itself. And you can see that the underlying layers are deformed around that rock. Okay, so what this implies is that this rock impacted the underlying material, and that the underlying material was cohesive enough that it deformed around that incoming clast or incoming rock. And so we see these features in volcanoes on Earth that form through explosive magma-water interaction. And so this is a feature that we've interpreted to be what's called a bomb sag. And so this is the bomb. It's a volcanic bomb. And here's an example of a location on Earth that has a similar kind of texture. This is from a volcano in New Mexico, where you can see we have a bomb that is that has impacted the underlying material, and it has deformed. And that in order for it to deform like that, that requires cohesion of the underlying material. And that cohesion must come from the presence of abundant water. We also saw other evidence of water-rock interaction, even at high temperatures. And so this is a mosaic image that shows Spirit's final resting area. And by that, I mean that we lost contact with the rover at this particular site. You can see that the area is covered with this reddish brown soil. But what happened was that the rover's wheels got stuck in this underlying whitish stuff. It's really powdery, it's really slippery, and the wheels churned it all up. And you can see that there's regions where it's more white, even areas where it's yellow. And we were able to see that this is hydrated iron sulfate minerals. And the way that we think that these formed is by fumarolic activity, where high temperature gases were released or escaped and interacted with the near subsurface or at the surface itself. And so, as an example, here are some fumaroles on Vulcano in Italy for you to get a sense for what these features may have looked like on Mars. Okay, so Spirit was super interesting, but we lost contact with it in 2010. The next rover that I want to talk about is the Opportunity Rover. And the Opportunity Rover found a lot of layered rocks, and these are sedimentary rocks that were deposited by water. And the layers that we see, the fine grain size, this is all evidence that it was laid down by water. Another feature that we see are these, you can see this rough surface to it. And what those actually are, when we look up close at the micro scale, so this is a microscopic image. This image itself is 3 centimeters across. And you can see these rounded features included within the rock. So here's one that's just popping out, but there's one here as well. And what those reminded the science team of are blueberries and a blueberry muffin. So we refer to those as blueberries. But what we found is that these blueberries have high concentrations of the mineral hematite. So this is what we saw from orbit, were these features actually included within the rock. And these are features that we understand pretty well because we see similar things on Earth, where mineral grains basically hosted within the rock, as water percolates through pores and as the sediments are being turned into rock, iron oxide will form around these to make spherules, okay? And we refer to these as concretions. So this is good evidence that water percolated through pores to make these features. Another feature we see are crystal casts. So you can see this is a rock from Mars in the background, and you can see this sort of hash mark cut throughout it. There's also scattered blueberries around, and so these little blue things, they do look like blueberry muffins, particularly in this image. But you can see these hash marks here. And what those are areas where we think minerals were formed, or where minerals were present, and where they have since been removed. and they now look like crystal casts. So areas where there was once a mineral present, and then it was dissolved away by later water activity. Okay, and we see these on Earth. Here's an example of crystal casts in a rock on Earth. We don't know exactly what those minerals are that made those crystals, but one good guess for what that might be would be the mineral gypsum, which is a calcium sulfate mineral that you guys know and love pretty well as sheetrock. Okay, so gypsum is a pretty common mineral here on Earth, and we've identified it on Mars as well. So now let's move on to the Curiosity mission. The Curiosity mission, the objective of this mission was to explore and to assess a region on Mars's surface as a potential habitat for life, past or present. So included with this was the idea that we're going to have biological potential. We're going to study the geology, geochemistry, the water, weather, and climate, as well as the radiation levels at the surface. And like I said, for the Spirit and Opportunity rovers, the Curiosity mission, the basic structure of this rover is pretty similar. It has the mast with the cameras on it. It has 6 wheels. It has the arm on it with a suite of instruments. But one of the things that makes this mission a little different is that it has the ability to actually drill into the rock, collect a sample, and then deliver those samples to instruments in the rover's body. And we can use that to measure isotopes as well as the mineralogies to find out what minerals are present. And so I've been a participating scientist on this mission since 2012, and this mission is ongoing, and exploration is still going strong. This rover, you can see that it is bigger than the previous rover. It's about the size of an SUV. So where was this rover sent? It was sent to a place called Gale Crater, and this is a image showing the surface of Mars, and it's shaded to show you variations in elevation, so that the high areas are in reds and yellows, and then the low areas are blues, purples, and even whites. And you can see that in Gale Crater, this is actually one of the lowest areas in this region. And this is where, if water were to collect, we would expect it to go into this region. Another feature that you definitely can pick out is that there's this boundary here between the southern highlands and the northern lowlands of Mars. The southern highlands have a lot more craters on it, and it has an older surface. There's a lot of evidence of water activity around this margin. You can see stream channels that sort of flow into this area. And the northern lowlands have relatively fewer craters. This means that it's younger, and that and one interpretation for these northern lowlands is that possibly at one time it contained an ocean. Now, keep in mind that that is still controversial. It is not uniformly accepted. I'm still ambivalent to whether or not there was once an ocean on Mars, but that's just one idea that's floating around. Okay, so Gale Crater is located here, right on this boundary between the southern highlands and the northern lowlands. And also included in the interior is a mountain. Okay, and that mountain, you can see it from another view. This is the side view looking at Gale Crater. And this mountain is made up of layered rock. It is 5 kilometers tall. And the strata at the lower section, or the layers of the lower section, vary in mineralogy and texture, suggesting that they may have recorded environmental changes over time. So early on in the deposition of this package of layered rocks, We see evidence of abundant clays, which suggests a more neutral conditions, possibly more favorable to life early in Mars history. And then later on, as we climbed up, as we've been climbing up and also from orbit, we can see a higher proportion of sulfate minerals that would form under more acidic conditions, probably less favorable to life. So there's this very major global climate change record that is preserved within this sequence. Oh, I should mention that this mountain does have a name. We call it Mount Sharp. So what did we learn from the Curiosity mission? What are we still learning from the Curiosity mission? Well, we see lots and lots of layered rock here, and it is very fine grained. It's mudstones that are interpreted to have formed within a lake setting. And they are dipping from the crater rim towards the center of the crater, which suggests water lane deposition. We also see, this is a microscopic image of a rock, and you can see these lenticular crystals. And these are known now to be gypsum crystals within the rock. And they are thought to form by evaporation. So periods when the lake was evaporating. And these are really reminiscent of those crystal casts that we saw, that the Opportunity rover saw in Meridiani Planum. Also within the layered rocks, we see spherules. So this is a mudstone, which is a very, very fine grained rock. And you can see speckled throughout here are these larger grains. And these spherules are reminiscent of the blueberries we saw in Meridiani Planum. And these are evidence of water percolating through pores. Another feature that you can see in this rock outcrop are these light toned veins that crisscross it. These also contain gypsum. And so this is evidence of water flowing through fractures in the rock and forming minerals within those fractures. So we take all of the evidence seen together to reconstruct what we think was a lake, a Gale crater. So this is the interpretation that's been put forward, that Gale once contained a lake, and that river systems draining the rim of Gale crater basically fed this lake system. So now you guys are probably wondering what's going on with Perseverance. How is Perseverance different from the previous missions? So this mission has a lot of similarities. It looks an awful lot like Curiosity, doesn't it? It has the 6 wheels, it has the mast with the instruments on it, and it has this arm. It has a large arm on board. But there's some pretty fundamental differences to this mission. And the objective of this mission is actually to find evidence of past life. And this raises the bar significantly because we recognize that a rover is limited in its ability to recognize past life. And so in order to achieve this objective, this rover is actually tasked with going out and collecting samples that will eventually be returned to Earth. So what this arm has on it is a drill system, and this drill is going to collect samples that will be delivered to the body. And here's what these samples are going to look like. They're going to be held within these canisters. And those canisters, we have a number of different canisters that are going to be filled. We can collect up to 30 samples, hopefully 20 of which will be returned to Earth. And this, how will those samples be returned to Earth? Well, what's going to happen is the Perseverance rover is going to drop its cache of samples onto the surface. And there's going to be future missions that are going to go and collect those samples. So there's this fetch rover that is going to go out and collect those samples and then deliver those samples to a lander that is going to contain an ascent vehicle that will eventually launch those samples into orbit around Mars. Once they've reached orbit around Mars, there will be another mission that will send an orbiter, possibly involving humans, to go and collect those samples from orbit. So you can imagine this is all very complicated, and Perseverance just represents the first stage in this. But if all goes according to plan, we will have samples returned to Earth by 2024 or 2034. Another big way that the Perseverance is different is that it includes this Ingenuity helicopter, and you've probably seen news articles about this. Maybe you've even seen videos. This is a helicopter that is basically a proof of concept to test whether or not we can fly a spacecraft, a rotorcraft on another planet, because it hadn't been done previously. And so this rotorcraft is, it includes cameras on board, but mostly it was just, you know, a test of engineering. And the idea is that eventually these kinds of rotorcraft might support future human exploration of Mars. Okay, so we want to have these things up and going. And on Earth, we geologists are starting to use rotorcraft like this more and more to help with mapping. So where was the Perseverance rover sent on the surface of Mars? You can see here that it was sent along this same similar sort of boundary as where Curiosity was sent. The boundary between the southern highlands and the northern lowlands. And it was sent to a place called Jezero Crater. Jezero Crater is a smaller crater than Gale Crater. So it's about 60 kilometers across. And what makes it unique is that it contains this stream channel system that empties into it. And it has a stream system that drains it. So it suggests that this is an area where water was held and it was drained away. And so this is a place that once contained a lake. Another feature that's significant here is that right at the mouth where this canyon system empties into Jezero Crater, there's this platform here. And this platform is interpreted to be what's called a delta. So a delta is a platform of sediments that form at the mouth of rivers. And you guys probably know the most famous one, the Mississippi Delta that makes up Louisiana, the southern part of Louisiana. Okay, so in that case, the Mississippi River is emptying into the Gulf of Mexico. And as the stream system, the river system slows down as it empties a larger, more quiet standing body of water, it will lose energy and then drop out its sediments, building up a platform of sediments. Okay, and so we're going to explore that delta system as well. So 2020 was launched in July. It was launched during a global pandemic. For one, we didn't know we didn't want to hold off on sending it just because of a pandemic, because we didn't know how long it was going to last. The other thing, though, is that Earth and Mars were lined up really well relative to one another. And so we have these launch windows that don't occur very frequently. And if we miss this launch window, we'd have to wait a long time before we could send the rover again. So here's a an image that shows the journey. So at launch, we ascended from here, and we wanted to line up very well with Mars at arrival. So here's Earth at launch, Mars at launch. And so we wanted to line up and take the shortest distance to get there. And it took about 6 months for Perseverance to arrive at Mars. How did this rover land? I'm sure you guys have seen videos and images of this, but I'll just go through this quickly. The idea is that the spacecraft first entered the Mars atmosphere at an angle, which allowed it to slow down a little bit, and this heat shield at the front sort of bore the brunt of that quite a bit. So this heated up, and that allowed it to slow down a little bit, but then it deployed a supersonic parachute, and that parachute slowed it down even more and removed the need to have this heat shield on it. So the heat shield could be dropped away. And once the heat shield was dropped away, the rover could finally image the surface of Mars. And we had, this rover was very smart in that it has an AI system on board that allowed it to select its landing site. So it looked at the roughness of the surface, it looked at the frequency of rocks at the surface, and it narrowed in on a place to land. Okay, and this was all done without Earth in the loop. Once it locked in on its place, it dropped away from the parachute. And this is what's called the sky crane. And this sky crane sort of coasted down. You can see there are these reverse thrusters that are blasting and allowing it to hover. And then it lowered the rover down on a tether. Once the rover touched the ground, those tethers were severed, and the sky crane could go off and do a controlled crash landing safely away from the rover itself. And everybody was excited. This was a very emotional time for many people, myself included. And I just remember jumping up and down, being so thrilled to be able to share this with my family. And when we got the first images down, you can see that it's sort of gray and not too exciting. But what this is a very simple image, low bits, that allowed us to get this image directly linked to Earth, downlinked to Earth. This is an image taken by a hazard avoidance camera that is located underneath the rover itself. So this camera is generally used for allowing the rover to drive around and not run into big rocks. But there's also this dust cover on it, which was meant to protect it. And once we remove that dust cover, you can get a sense for how much better the cameras are. And you can see that the rover's shadow here and the wheel on the ground. So these were two of the first images that were taken. But once we were there longer, we were able to take some really amazing 360-degree panoramas using the NavCam Z instrument. And so this is the first panorama that we were able to see. You can see these are regions that were actually scoured away by that sky crane. And as the reverse thrusters were basically blowing rocket fuel downward, we actually were able to excavate the substrate, and you can see there's some bedrock that is exposed there by the sky crane itself. Also, off in the distance, you can see this is the delta, and that is this is going to be one of the primary targets for this mission. So it was really nice to see that early on. We're still trying to understand the rocks in this area. So I wish I could tell you a better story, but we still have an ongoing debate about how these rocks formed. And you can see that these are some images of the first rocks we're able to image. They're gray rocks. We see things that look like they might be crystals. We see things that might be clasts. And we're still trying to understand how they formed. We'll have a good story for you pretty soon, I hope. The landing site was here in this region. So this is an orbital image of Jezero crater. Here is the delta. Here is the landing site. And we named the landing site after Octavia E. Butler, who is a science fiction writer. We name landing sites after notable people in science fiction, actually. So the Curiosity's landing site was named after Ray Bradbury. And for those of you who don't know Octavia E. Butler, I highly recommend checking her out. She was somebody that I hadn't read any of her books previously, but since this naming, I've gone out and read a couple of her books, and they're awesome. Really interesting. So this is the site, and when we first landed, we wanted to check it out. But first we had to drive someplace to go and drop off the helicopter and do some testing with the helicopter. So one of the first big campaigns that we've done was to drop off the helicopter. So the helicopter was located underneath the rover's belly, and we needed to find a safe place to drop it off. And so there it is. This is actually a selfie image taken by the Perseverance Rover using cameras located on the rover's arm. And there it is. It looks so cute next to Perseverance. So here's a video showing the first flight of Ingenuity. And back down again. Isn't that cool? I can play that again. So this is the first time that a spacecraft or a rotorcraft has been flown on another planet. So a very, very cool thing. So we've now done, I believe, 6 flights, and we're planning the 7th flight. And so now, and so we've done a series of test flights. This is an image taken by the helicopter itself on its 3rd flight. And one of the cool things about this particular image, it looks kind of featureless. You see some sandy substrate, but off there in the distance is actually Perseverance. So it's kind of cool to have Ingenuity image Perseverance. And here it is a little bit closer up, or a little bit more blown up. As the helicopter is continuing on, we've been able to take videos of its flight. So this is one showing the 4th flight, and you can see how the landscape is sort of moving around beneath it. And then here's an image of from the 5th flight. So this was actually taken by the Perseverance rover, capturing it just up here against some hills off in the distance. So now that we've been able to prove that Ingenuity can fly, now we've actually been able to transition Ingenuity into another phase of its life, where it's actually going to help scout for the Perseverance rover. And so that's super helpful. And the Ingenuity helicopter is actually lasting longer than we anticipated. So it's kind of like we have this bonus sidekick. And so here is what the terrain looks like that Perseverance has to navigate through. You can see that there's a lot of boulders around that we're going to have to go around and figure out how we're going to get how we're going to drive. So driving is a little bit slow right now, but eventually it's going to pick up and we're going to explore. We're testing out all our instruments. So some instruments haven't had a chance to actually analyze rocks yet. But this is a microscopic image of a rock. And you can see basically we're going closer and closer and closer up into this rock. And so where are we going to go next? So we deploy the helicopter just north here. And then now the next idea is that we're driving south and we're going to collect a sample. So we need to do our first sample to sort of test out our sampling capability. We hope to collect a sample of this cratered area. And hopefully that sample will be datable and allow us to help constrain the time scale of Mars. And the other thing that we're interested in is this feature here called CETA. This is an area that is lower in elevation and there's layered rocks that are exposed along the margins here. And so we're hoping to be able to go into CETA, check it out, and maybe come back out. And then we'll carry on towards the delta. So thank you for listening. I'd be happy to take any questions.
Hi, Mariek. A couple of questions here from the group. Somebody said, Cameron said, sorry, I missed it. Are these flying copters equipped with LIDAR technology? If I'm saying that wrong, I'm sorry. Do you know if they have hyperspectral sensors?
No, not these ones. So it has a camera. It's a really basic camera. So he was asking about LIDAR.
LIDAR.
So yeah. Oh, no problem. This is, so there's no hyperspectral capabilities for this particular this spacecraft, but presumably future rotorcraft will be equipped with that kind of capability.
Okay. And he also asked, do you know who developed the AI on board the rover?
Oh, people associated with JPL. So the Jet Propulsion Lab in California. So I don't know exactly who did it.
Okay, he said that makes sense.
I'm a geologist, so
yeah.
I'm not involved with that side of things. It's a huge mission. So there's scientists all over the planet that are involved with this, but also a really big team of engineers that actually built the rover, and then the programmers and all that are actively involved with keeping the rover going.
Okay, I have a couple of questions that are a little less scientific, maybe. When you mentioned the authors, you mentioned the Ray Bradbury. Which mission was that from? That's the landing site, right?
Yeah, that was the landing site for the Curiosity landing site.
The Curiosity landing site. Okay, thank you. Someone is saying, I just want to clarify, is the only evidence for past life to be determined from the samples that come back to Earth, or is there other potential evidence that can be determined while on Mars?
That's a really good question. Okay, so we have the capability to measure organics on Mars. And so if we were to find complex organics that under certain circumstances might point towards a biological origin. However, the bar for that is pretty high. And so that geochemical signal is one that we'll be looking for. And the Curiosity rover on the Mars Science Laboratory mission has been sort of looking for that all along. Up till now, we've only found kind of simple organic molecules, but they're there. We do see organics, and the problem with organics is that solar radiation destroys it. So you have to have the right set of circumstances to get preservation of those complex organics. but the other kind of thing that we might see would be if we were very, very lucky to encounter something that like what's called macro fossils. And so those would be fossils that we could actually see with our eye, as opposed to micro fossils, which are so tiny you would need a microscope to see them. So on Mars, I wouldn't expect to see, clamshells or anything like that. However, there is a possibility that we would see something like what's called a stromatolite on Earth. And what those are layered algal mats. Is basically mats of blue-green algae that collect sediments. And we've seen these kinds of stromatolites from very, very early on in Earth's history. And so it's possible that features like that could have occurred on Mars. We have not yet seen it, but we're, keeping an eye out, and it's possible.
Thank you. You mentioned that there may be a human component to the collection part of the mission. If the opportunity arose, would you want to go?
Personally, no, thank you. But I can understand why some people really want to go. So it would be, it would be the opportunity of a lifetime. I'd rather just, read books about exploring Mars. So I'd say that it's too far away. I'd be too far away from my family to want to do that, risk my life for that. Yeah. It's also kind of cold and isolating. And I think that it would actually, I think I would be feel kind of claustrophobic being in a spacecraft for so long.
Definitely.
To get there.
Definitely. You mentioned a launch window, that they're few and far between. What constitutes a launch window?
Where's that picture? It's where when the Earth and, here we go. So basically where Earth and Mars are close to each other, when their orbits are aligned. Oh, okay. And that's what that refers to. And so one thing I should mention is that this launch window was utilized by other space agencies, not just NASA. So there's a number of different missions that have been arriving at Mars lately. So the United Arab Emirates sent their first mission to Mars. And they sent an orbiter. There's a new Chinese rover, which is very cool, that has arrived at Mars. And then, so yeah, it's an exciting time for Mars exploration.
That's awesome. Another question. Hold on one second, sorry. What are the other theories on how the northern lowlands were formed, aside from once being an ocean of water?
Well, there's a lot of ideas. One could be that it was a massive impact. There's other ideas that the whole northern lowlands were just completely resurfaced by lavas. So there are a number of different ideas for how it could form. And I can never pretend to be an expert on all those different things. Yeah.
That's a big question.
It's an interesting and ongoing debate within the Mars community.
Okay. You mentioned that Mars once had a molten core and may have at one time been similar to Earth. It is my understanding that Earth's multi-tectonic system is due to its molten core, along with celestial object impacts. If this is the case, how is Mars still a single tectonic system? Or is my understanding of Earth's tectonic origins incorrect?
Okay, so good question. So yeah, Mars has only a single tectonic plate, whereas Earth has many tectonic plates. And so the the tectonic plates refers to the outer parts of the Earth that move around relative to one another. So in some cases they bump into each other, in other areas they move apart from one another. Okay, and so what drives that on Earth is not necessarily the core, it's the convection within the mantle. By convection, I mean that the hot interior of the mantle actually rises up, and then it spreads out and cools down, and then it sinks. So we're actually on Earth, the mantle is constantly stirring, but it happens on very, very slow time scales. It's like the time scale that it takes for your fingernail to grow. Okay, so it's not really molten. It's actually that it's more deformation of the interior. It's very slow deformation of the interior. Okay. Whereas on Mars, Mars also experiences mixtures of the interior, but it has what's called a stagnant lid, meaning that it is all one tectonic plate. And where it is experiencing upwelling in the interior is actually focused here, where there are in what's called the Tharsis region of Mars. And this is where we extremely large volcanoes. So Olympus Mons is a volcano that is the largest volcano in the solar system, and it has it's the size of the state of Arizona. So it's a huge volcano, and there has to be, and you can see there's this broad area of uplifts surrounding these large volcanoes. And so what's going on is that you have upwelling of warmer mantle material that's basically supporting those volcanoes, and as it rises it melts to create the magmas at these volcanoes. That's not to say that these volcanoes are expected to erupt anytime soon. We think that the last eruption at one of these volcanoes was probably about 2 million years ago, and it could conceivably erupt again in the future, but just not within our lifetime. I wouldn't expect it to be within our lifetime.
Thank you. We have another question. What type of research are you personally doing with this mission? How often do you get images or data?
Okay, so for the Perseverance Rover, what I am doing right now, I just want to pick up a rock. I'll show you a picture of a rock. Let's do this one. Okay, so I'm involved with an instrument called the Pixel instrument. Can I just stop this thing from, I can't get it to stop zooming in. Okay, so I'm involved with what's called the Pixel instrument. It is an X-ray instrument, basically X-ray fluorescence. And what it does is it measures the composition of the surfaces of rocks. And this is an instrument that is located on the rover's arm. And right now, because it's relatively early on in the mission, the Pixel instrument has not yet been deployed on a rock. However, it has been deployed on the rover's body itself on what's called a calibration target. And right now, what we're interested in is looking at this powdery stuff on the surface, which is the dust. And we're looking at how that dust, what the dust is on the surface of the rover's body. And comparing it to previous measurements on Mars and taking other places. The other thing that we're interested in is seeing if we can use that to understand the chemistry of the dust in order to sort of constrain compositions of dusty bedrock. So we have this bedrock here that is very dusty. I'll zoom to a place that's not so, it's sort of bothering my eyes to see that. But you can see that there's dust scattered everywhere on the surface of Mars. And we're going to be able to abrade and remove some of that dust, but in some cases, it's not always going to be possible. And so what I'm interested in is whether or not we can use the chemistry of the dust and do some, basically some look at mixing of the dust with the underlying material to sort of understand the chemistry of the rock. So that's what I'm actually looking at right now.
Okay, thank you. Oh, thank you, Cameron, for your pointer on how to exit presentation mode and then stop the Zoom. I think that was for what it was zooming in. Does anyone have any further questions? Okay, I don't see any more questions. Thank you so much, Mariek. Thank you for sharing all of your knowledge. I'm a little, I feel like I have to go do a ton of research because you've given me so much to think about. And thanks everybody for joining us tonight.
Sure, you're welcome. Thanks for having me.
Thank you. Everybody's saying thank you in the chat. I'm not sure you can see it.
Oh, I just haven't been looking.
Oh. Thank you very much. Take care.